All right, let's go ahead and get started. First, I want to thank everyone for attending today's webinar. My name is Aaron Bartlett, and I'm one of the account managers here at Qnect. And I'm joined today by Josh Hines, our technical field manager. We're going to cover a number of topics surrounding best practices on job workflow to communicate your project's progress. Now, a quick reminder before we start, all attendees are in listen-only mode. If you have a question during the presentation, please feel free to use the Q&A section in the chat tab to the right. With that said, let's discuss our objectives for today's presentation. First, we'll start by discussing model preparation and how to get everything ready for Qnect. We'll then talk about following the prescribed checklist when it comes to a run through Qnect. Following that, we'll spend some time discussing the reports and outputs that are available and how to analyze them. And we'll round that out with a discussion on what to do when you've completed your Qnect runs. This includes what templates are available and what additional outputs can be created. With that said, Josh, I'd like for you to take over and walk us through the first section in today's discussion around model preparation.
Okay, the first topic we will touch on today is model preparation, how to best prepare your model prior to running Qnect. First, we will look at extending framing. We will be looking at beam-to-beam locations, beam-to-column locations, and cantilevered locations. So as you can see on the top right-hand side, those are incorrect. And on the bottom, you'll see that those are correct. So when extending a beam-to-beam, we want to make sure the beam that is going to be supported is extended to the center line of its supporting beam. Same thing with a beam-to-column. We want to make sure that those beams are extended to the center line of the column supporting them. And finally, with cantilevers, as you can see in the bottom left-hand corner of the correct picture, you'll notice that the beam vertical in this view is going to extend to the center line of the cantilevered beam, and the cantilevered beam will also extend out at least flush or past the beam that's framing into it. Now let's look at column extensions. So we're going to extend columns to the top of steel locations, and if you have a splicer, they go above top of steel, that's fine. Extend them where you need to, and then underside locations. So as you can see on the top right, that is incorrect, and on the bottom right, those are correct. So you will make sure that you extend any columns up to the bottom of your steel, and you will also extend any columns to the top of steel. We don't want those sitting at a midspan of a beam. There are some default extending tools in Tekla. You can go type extend in your macros, and you will find the extend tool, the extend beam to columns tool, extend beam to vertical planes, and then extend adjust elevations. Next, we will look at start and end handle locations. So as many of you know, start and end handle locations are very important when you're looking at a beam or a member on a shop drawing. It always goes from left to right for a beam, and that is your start and end handle. So as you can see in the incorrect view, you'll notice all of the end handles are on the left-hand side, which is incorrect. And in the correct picture, you'll notice that all the start handles are on the left-hand side. So it's best practice to make sure when modeling that you have a left to right approach in a plan north and also a bottom to top approach in a plan north. There's also a swap handles tool within Tekla. Go to your macros and type in swap. You'll be able to go find that. And it is very important when swapping handles, the UDA fields will remain and will not follow your handles. So if you have something in a UDA field in a start handle location and you swap that because the handle was in the incorrect location, that UDA field will not move. It will stay true to the start. So make sure when prepping your model, you pay attention. Next, we will be looking at placing reactions in a UDA field. So we'll be looking at shear reaction locations, axial reaction locations, and moment reaction locations. So when you need to place a reaction into the model, you're going to go ahead and do that through the UDA fields. So as you can see here, you're going to place the shear reactions. And then for axial, we're actually going to locate two places. We're going to put a load reaction in the tension as well as compression. Now for moment, you're going to go ahead and put the reaction in the moment location, but you also need to make sure that you check the box to yes where it says moment connection symbol. Because if you have a reaction in there and that is still checked as no, it will not actually try to complete a moment connection at that location. We will simply just move past. All right, next we're going to look at spandrel beam locations and placing those in a UDA field. So what Qnect considers a spandrel beam is going to be something like a perimeter beam going from column to column, or it could just be a perimeter beam where you're looking to place a full depth connection, whether that is going to be an actual full depth shear plate, or if that's going to be a maximum bolt row double angle connection. And you also have the ability to say, yes, you do want a backside full depth stiffener. So as you can see in these three demonstrations, you'll notice we have spandrel turned on in our UDA field as yes. And then in our preferences, we would also turn on yes for the full depth connection, and then yes for the full depth backside stiffener. Okay, next we are going to look at erection tab locations. So we'll look at a near side, a far side, and then we actually have something coming out very soon, which I think most of you will be pleased with. So, as we touched on before, start and end handles are very important. This is another one of those reasons why. So if you go to your start handle at a location like this, and you go to the UDA field, shear plate, or single angle relative to beam, and you go ahead and say near, you are now going to see your connection on the near side. Then, if you were to show that as far, you will notice that that is on the far side. We've gotten a lot of questions about, is there a global approach to do this? So, as always, we try to listen to our customers and provide as much as possible. So coming very soon, you'll be able to actually do that as a global approach. So in your preferences, you would set up how you want your locations to be placed, and then you would simply just adjust the minimal locations required in the model. Okay, next we will be looking at embed plates. So when we prepare a model for Qnect, and we're going to have an embed connection, we actually have to place an embed at that location. So we're not worried about studs on an embed. They can be there, but when we place this in here, we want to make sure we have a viable, usable plate. And if you'll notice there's no plate on the top. On the bottom, there is a plate. That is exactly what we need. And there will be scenarios where you may get into an environment where you have to provide a dummy plate. So say you have two channels that are butted up together, that's going to act as an actual embed. Well, what we would need at that point is a plate placed in there, and you can put it in a filter for a specific class that gets turned off. But when you go to select it for Qnect, it's there for you to select the beam and that dummy plate to actually create that connection. All right, the next topic we'll look at is the naming conventions. So we work with naming conventions. If you want us to look at certain members to be able to try and connect them with Qnect, beams, columns, embeds, hangers, posts, so on and so forth, actually have the exact name shown here that needs to be placed in the UDA field. So for instance, if you have a post, then you want it to be called post. Now, we also have the ability with non-composite beams to be able to distinguish a composite versus a non-composite. Depending on your load criteria, you may want to do that. So you would want to place non-composite in that name field. That's going to be a lot easier for you rather than going to the field stud location and placing studs in a UDA field at each member. That'd be a lot more time consuming. Although that is an option instead of the naming convention, this is a much faster approach. Okay, we have one final model preparation tool that has been added more recent, and that is connection type adjustability in a UDA. So when we set up all of our preferences prior to running a model, we use a hierarchy system here at Qnect. So if you have a beam-to-beam connection and you want to set that up to have a single angle bolted connection, we'll go ahead and put that first. Now, if that connection cannot be met per the design criteria of that project, and you would like it to then try to complete that connection with a shear plate, that's how we would set it up as shown. And then it would go down the line if it couldn't do a shear plate to a double angle. And if it couldn't do that, it would go to an extended shear plate. And then if it couldn't use any of those, we simply would not place a connection in the model. Now, you do have the ability while prepping a model, if you know that there will be certain specific connections outside of that global hierarchy approach that needs something else, you can go ahead to your UDA field at your start and end handle locations, yet again, very important, and you can manually select something like shear plate here. So at a location where shear plate would be tagged, you actually would have the shear plate location connection at that location rather than trying the hierarchy system. But keep in mind, if you do have a shear plate called out there and it cannot meet that connection, it will no longer try any other connection that's in that hierarchy system. It will only try what is in the UDA field. Okay, next we are going to get into following the prescribed checklist. In this checklist, we will go through a start to finish approach using Qnect in a Tekla structures model. So we've already gone through how to prepare your model. So we will go ahead and prepare our model, and then we will move into preference setup. So for preference setup, we are going to go in to the design documents, find out all the criteria required to set up our preferences, whether there are loads indicated on framing plans or maybe in the general notes. We are told to use a UDL factor, so on and so forth. We will also look at material grades, bolt sizes, all of that type of information to go ahead and set up our, to go ahead and set up our preferences online. Then we will get into the initial run. So most of our clients will do one initial run, and then they will start vetting the remaining connections. So to do an initial run, we either select the entire model or an entire sequence that we're going to be starting with in that model. Go ahead and do button 1, button 2 to bring that information back in. And then we will get into connection data analysis. So typically we will get into reviewing reports, looking at no connection reports to find out why certain things did not connect. And then we typically go back into the preferences, make some revisions if needed, or re-prep some things in the model. And we can then rerun, whether it is an entire rerun of the initial run, or whether it's just vetting any other connections that could not be completed in that initial run. And in most cases, we will be able to increase the connection joints in doing so. Okay, the next item to discuss will be analyzing the data, as mentioned in the previous checklist. Okay, when analyzing the data, we're going to look at reports. So we have a few reports here: the job standard summary report, no connection summary report, a POP or preference optimization comparison, BOP or bolt optimization comparison, and beam web doubler reinforcement report. First will be job standard summary. Okay, this is the job standard summary sheet or report, and it gives you an overall of your project for your initial run. So as you'll see here, you have beam-to-beam connections that are single angle bolted, and also beam-to-beam connections that are shear plate. There are 55 of the single angle connections, and there are 36 of the shear plate connections. You'll be able to notice beam to column flange, beam to column web, beam to embed, and beam to HSS connections. Now, if you were to go into one of these ID location areas, you will notice group IDs and then calc IDs. So these are links that will take you to the long calc information. There's a group that will take you to the actual group. So for instance, you only notice one actual connection in here, and that's because there is only one W40 by 149 framing into a W40 by 167. If there were multiple, they would all be in here. You will also be able to look through this document to find out if that member is sloped or on a pitch. If it is skewed outside of a 90-degree angle, you'll be able to find the actual span, the reaction requirement, the capacity, and also bolt information, connection material information, top and bottom cope information if required, beam edge distances, and then reinforcement plates, so on and so forth. So reviewing this information, making sure it is accurate, will really let you hone in on adjusting anything that may need to be adjusted to revise any of your Qnect runs. Let's now move on to the no connection summary. Okay, now we'll look at the no connection summary. So as you can see, there are 172 connections that were successful. And then let's dig in and find out why some of the connections that did not appear could not be connected. So for instance, if you look, let's go to 18 of these were part of a group with moment connections that were turned off on the minimum job requirements page. So we may have had moments in there, and when doing an initial run, we wanted to turn them off. So that's exactly what we did. So now we may want to go turn those back on and rerun. Then supported connection type not found. So that's a type that would not be in our library. Same with the next two, a column to beam connection. There's a specific reason why it's a connection that we don't supply. And then a column splice. Currently in our library, we do not do column splices. And then there are 8 members that are part of a group with load computed with UDL is too high. So what that's telling us is we have used a universal design load factor that has been provided to us or that we have used to qualify. And because of that, the actual capacity, the actual reaction is too high for us to meet with the capacity. So at that point in time, we may want to write an RFI to be able to find out if we can get the actual reactions on a project. You will also notice there are 3 more, same type of a deal. And then at the very bottom, this happens from time to time, and this is definitely why we vet the connections after an initial run. You will notice there is one beam-to-beam connection that is too close to a beam-to-column connection. So because it is in tight quarters, we would actually go back after the initial run and select both of those beams, the supporting beam and the beam that needs to be supported. We would rerun, and in most cases, we would be able to actually achieve that connection. All right, now preference optimization. Preference optimization comparison report. We have the ability to run 9 iterations of the same project in multiple connection type preferences. So what that may include is your baseline per design may be a shear plate design for beam to beam and a double angle for beam to column flange. But we have the ability to run that in multiple different ways to where we could have beam to beam be a single angle, bolted, bolted. Beam to beam be a double angle, welded, bolted. So we can switch things up, run 9 different schemes with different bolt variations and spacing. We don't have to include bolt optimization in that, but we can. And this is the results that you would get. We would show in our first run, if we did use bolt optimization along with preference optimization, we were able to connect 39 connections, and we were only able to do 38 connections with this standard. The next run was 40 connections compared to a 36. So we would do that. We'd be able to go through all of these 9 different runs, and we would then come over here and look at the baseline. We can click on that. It'll take us to the baseline report, that job summary report, or we could go to any of these other ones and select those as well, and it would do the same thing. It'd take us to those specific connection variations to be able to put time and cost to. Okay, our next report will be bolt optimization comparison. But before we get there, I just want to let all of you know, you probably saw some weird spots in the previous report, maybe some blank spots. And that's because we always make sure to never release client privileged information. So it looked kind of funny, but I ended up hiding that information. So bolt optimization comparison report. Bolt optimization comparison and cost report. As always, we have taken out all company names for privileged purposes. And what you'll notice in here, well, I guess first off, what is bolt optimization? So here at Qnect, we have the ability to run the 3-inch vertical spacing in connections from anywhere from 3-inch all the way up to 6 inches in 1/2-inch or 1-inch increments, whichever you would like, to be able to reduce typically 20 to 50% of the bolts on a project. So once we do that and you get into this report, you're going to see the results of that, but also a lot more. So in here you can see material, and you'll see cost as you have in other reports. Keep in mind, these are the costs of what we've accumulated over time. These will not be your exact job costs. Those will need to come from you internally, or you can add your actual unit prices into our system, which will then populate in these locations. So for instance, you will see shear plate totals, web doubler totals, column web, so on and so forth. Let's get into some of the connection materials, and then you'll actually get into some of the copes, the welds, which we show the size of the weld, the type of the weld, the designation, how many there are, the length, all of that type of information. And we compare that from the optimized compared to the standard or baseline per design run. And we will bring all this information in. We'll look at the bolt counts. And then at the very bottom, highlighted in green, you will notice the actual quantities. So the standard bolt spacing, in this case, there were 35,894 bolts. And with using bolt optimization, just simply reducing the quantity, we were able to take that from 35,000 all the way down to 22,000. So we were able to save 13,847 bolts. So you really go into that type of information and think, what could that do if you're a detailer for your fabricator, for the erector, or if you're a fabricator, what could it do for me and my bottom line? Our final report to review will be beam web doublers. Okay, web doubler plate reinforcing summary. So what we're looking for in here is, you'll notice to the right hand side, your doubler plate itself. We're looking for the actual thickness and material, the width of that plate, and the length of that plate. So for instance, with this specific member, we're looking at a W12 by 19 that's framing into a W30 by 90. It requires a 56 kip reaction, and we are able to meet that with a capacity of just over 41 kips. So with the web doubler report, you're going to look at this and try to figure out if you're able to get to a third-party connection engineer or really your EOR to find out if, one, loads can be provided specific in locations if you're using a UDL factor, or if loads have already been provided, if in this case 41 kips instead of 56 would actually be feasible at this location. So this gives you the ability very early on to start looking at these locations and getting with the design team to see if you can actually reduce some of this information, in turn reducing web doublers or any type of required reinforcement. Okay, so that's the reports and the information you're looking for there. Then really just to capture everything that we were trying to review in some of those reports, welds, whether you're looking at it in a report or you're looking at it in a model for review. Also material sizes, thickness, that type of thing. So when you're setting up your preferences, you may set up your specific size that you are looking to use at a connection, but we also have iteration control. So for instance, if you have a 4 by 3 by 3/8 beam, 4 by 3 by 3/8 connection angle that you're going to use, but you have the ability to also put all the different types of sizes as a fabricator or as a detailer for your fabricator. You can put all the different types of sizes used by that fabricator, and we will not supply a connection if it is not provided in that iteration control. And then finally, bolt sizes, holes, slots, etc. So anything that you notice, whether it's in a model or online, you're going to make sure that the bolt sizes are what you expect. The holes, whether they're standard or slots, are in the correct material that you're expecting as well. Okay, our final topic, which will be finalizing the process. So we will be talking about deliverables within this process. First, let's look at 2D code maps. So generating the information from our connection codes with connection information for a faster review to put in a 2D code map per floor plan or per framing plan locations. To accompany that, we also have the ability with shop drawing references for those areas. So if you have connection code maps that are going to have a connection code specific to your start and end handles, you can also represent the same information on a shop drawing. Makes for a lot faster review with a third-party connection engineer or with the EOR. And then submittal packages, whether this is an internal submittal for review for a CE, connection engineer, or for an engineer to review when you send in your standard approvals. Same as cost comparison reports, as well as KISS files, IFC files, maybe some custom reports, could be FabTrol type files, Fab Suite, Strumis, so on and so forth. And finally, a viewer model. We have the ability to export our model into a viewer system. What you see on the screen at this time is Trimble Qnect, and this makes for a very useful tool if you are trying to supply a model for your client so they can physically see what you already have in a model, whether it is at proposal time or later in the game. And as always, if you have any questions or concerns, feel free to send me a text, call, or email me directly. Thank you for joining the webinar. And I wanted to actually mention, when we send out an email to give you access to a recording of this webinar. We will also be providing a link to a PDF document, which is the model preparation information we went through today. You can use that as a resource, kind of a step-by-step. So again, thank you for joining the webinar, and we will catch you on the next one. Thank you very much.